Okay, let's begin. So we discussed last time Wilson loops and their relation to confinement. And basically, to sum it up, when you have a gauge theory, the Wilson loop is a natural observable, and as a result, by looking how it depends on the loop, you can decide whether the theory confines or not, whether we have the behavior of the Wilson loop. At very large distances, it's what replaces. It's kind of a analog of correlation function of the when you have ordinary two-point function at large separation in massive theory, it behaves like e to the minus mu r. R is a distance. Here it behaves like e to the minus mu square, which is calculable in principle. In all those theories which we discussed last time, it is a calculable quantity. Basically it means that the energy between two charges grows linearly with the distance. It also implies that the physical picture which it implies is the following. It is that you have two charges, and when they are at very large distances, there is a string between them, and as time goes by, the string moves in time and sweeps certain area, and there's a natural action for string theory that which is called the Unruh action, which is that S is proportional to the area of the surface. So we have the loop, and the way to interpret these results is to say that there is a random surface attached to the loop itself. This is just direct analogy with a two-point function in the ordinary field theory, when we say the two-point function can be represented as a sum over all possible trajectories connecting 2 points. The natural generalization of this is to say that instead of 2 points you have a contour, you have a closed loop, and this correlation function can be represented as a sum over all possible random surfaces. Each comes with the action A of C. And physically, it means the following. Physically, it means that you have, I mentioned this already, that the flux lines collimate into the string, and there is an electric flux coming through the string. We will be discussing it next time in more details in connection with gauge string duality, but in the essence of gauge string duality is that you, instead of dealing with fields describing electromagnetic action, you replace it. It's not obvious that it's possible, but you conjecture that it can be replaced with the dynamics of the flux lines. The gauge theory gauge field theory is replaced with a replaced with a theory of flux lines, like flux strings. I shall. It might be. Well, maybe I should have saved it for the next time, but I will still just mention it, that it is not excluded that even at when we look at the standard model, we say that there are gluons, and these gluons can be also described by some string. But in this sense, there are strings which are exactly equivalent to fields. What I'm saying is that the conjecture itself is that there is equivalence between fields and certain type of strings, but it could be that there is that the fundamental definition of the standard model should be based on strings, on more general strings than these gauge strings. And in this case, we will discover, hopefully in the future, some not simply gluons, but some excited gluons, some excited partners of gluons. But that's a mere speculation at the moment. There are no signs, experimental signs that this will be happening. Still, it's interesting. And in any case, it's a win-win situation to have this formulation, to have this gauge string duality, because some problems are easier solved in the language of fields. Other problems are easier solved in the language of strings. But that we will be discussing on the next week. What we will discuss today is some other aspect of the Wilson loop, and more generally, we said that before that we can interpret superfluidity. We always discussed in parallel superfluids and confining theories. And we said that superfluidity can be interpreted as a frame-dependent vacuum, in the sense that we study what happens when you put the system in a box, or in a pipe, and then start moving the pipe itself. We'll go to the moving frame, and one of the key facts about superfluidity and normal fluid versus normal fluid is whether when you perform Galilean transformation you change the vacuum. If when you do this, and we saw that there's this condition that elementary excitation in the fluid, you have to come, if it is greater than PV, then elementary excitation will be created if it is less than PV. And so on. I shall not repeat this. Now there is a very interesting analogous phenomena in quantum geometry, in the geometry of gravitational fields. And that's what we will be discussing today. Namely, we will be discussing several problems more or less simultaneously. And one problem, the closest to this, is this one. Let's suppose that we have accelerated motion, that we have a trajectory of accelerated observer. I shall explain in a moment what means concretely. The question is whether this Cherenkov radiation will be present or not. Well, let me be more concrete here, and then we will move to black holes and to the de Sitter space. So let's remember what is the accelerated motion. It basically can be defined in many ways. One geometrical way is to say that we have in the rest frame, each moment at the rest frame of an accelerated particle, we see constant acceleration. But a simpler thing is to say simply that let's suppose that we have constant, imagine that the particle is charged, and we have a constant electric field. We, by definition, so the force which acts is constant. We call it by definition more or less accelerated constant acceleration, motion with constant acceleration. And it, of course, not surprisingly, it coincides with the geometrical definition that you go to the frame, through the rest frame, and observe the constant acceleration. So, if we have four-dimensional notations, we describe the trajectory. We describe the trajectory by the equation x mu of tau. When you have a constant electric field, let's suppose that we have 1 plus 1 dimension for simplicity. In this case, the tensor f mu nu is and you have the Lorentz force is it's just f mu nu x nu dot, and the solution of this is very simple. Let's set e to 1. The solution of this will be simply the what is called the hyperbolic motion. I'm just reminding you, and I'm sure you know some of this. So if we have x0 here, time here, space here, we have the light cone. We have the light cone, and the trajectory of the accelerated particles, its velocity becomes closer and closer to the velocity of light, is this hyperbola, which approaches to the speed of light. So we have any? X0 is time. What? X0 is time, yes. It will be clear in a moment. So we have x0, we can parameterize it as sinh tau. X1 is cosh tau. And we also can write it down as we can introduce x1 plus minus x0, which will be e to the plus or minus tau. And if we have, more generally, we have, there are of course many solutions depending on whether the particle was at moment 0 of time. So the more general solution will be not surprise. So this I will call x plus minus, and more generally x plus minus will be rho. Rho is this distance multiplied by e to the plus or minus tau. Now, We can now we have to define the accelerated frame. Each row corresponds to accelerated observer, and accelerated frame is just when you take a row as one of coordinates. So in this case, tau is in this accelerated frame. What is accelerated frame? It's the frame in which, or coordinates in which accelerated observer is at rest. So for him only, what does it mean to be at rest? Mathematically means that for him only time coordinate changes while the spatial coordinate kept fixed. Which means that these accelerated frames are given by the coordinates rho and tau. It's given by these coordinates, and so let's write down the metric in these coordinates. The first, before I write the metric, it should be clear what this coordinate means in the Euclidean space. If we go to the imaginary time, so that instead Lorentzian space or Minkowskian space, we have the Euclidean space. What this accelerated frame means? These coordinates. What?
It will be a radial.
Polar coordinates. You see, if you change tau to I tau, that would make you would make you Euclidean. X0 becomes imaginary, as you see. X plus minus will have they will be complex with this condition, x plus minus, x minus plus, and as I already mentioned some time ago, that's the Euclidean section of the complex space. The Minkowskian section, and we obtain it from the Minkowskian section, for which it is simply reality condition. In Minkowski, x plus minus are real. In Euclidean section, they are complex conjugate. And that's what you get by this substitution. Now, if you differentiate this relation, you get d rho e plus or minus tau plus or minus plus or minus rho e plus minus tau d tau. And finally, we have the metric ds square, which is dx plus dx minus, which becomes d rho square minus rho square d tau square from this formula. And it's quite clear that as you change tau to I tau, you will get simple polar coordinates for two-dimensional space. That's all preamble what I'm saying now. It's some rather trivial kinematics, but I need to set the stage. Now there's one more interesting thing about this. So this is the Minkowskian version of polar coordinates, and I also can write it down in this way. I can write it down as rho square d rho over rho square minus d tau square, which is e to the 2z d z square minus d tau square, where z is logarithm of rho. So you see these coordinates are conformally Euclidean, conformally flat, meaning that they differ from this only by this conformal factor. Now a slightly less a trivial matter. Imagine two observers. By observer, I mean this hyperbolic, a particular hyperbolic trajectory. And I want to compare the observer, the accelerated observer, and the observer which is at rest. The world line of the observer at rest is this one. The world line of this guy is here. And now imagine that there is here, obviously, there is a phenomenon, very important phenomenon called horizon. There is a horizon in these coordinates. By horizon, one means inability to transmit signals between two observers. So that's more or less generally that if you have somewhere some two observers and one cannot send signal to the other, that means that there is a horizon for the other observer. Tell me which horizon we have here. Here we have, this is the simplest example of the metric with a horizon. So who cannot send signals to whom? Imagine light signals. What?
Observer from inside light will also.
Observer.
Yeah, inside light cone cannot signal to us.
Well, but who will, suppose this is observer A, this is observer B. So who will see whom? One observer will see another, but the other will not see the first one.
A will not see B.
Not quite. It's the opposite. Indeed, look, suppose this guy send a light signal. It sends a light signal. It never reaches the observer B. While the signal from the observer B, it will reach eventually the observer A. But that's kind of it's very important feature of this thing, and as you will see, related to the properties of the Wilson loop. And we want to figure out what is happening. First of all, let's now this is, I assume, is a common knowledge. You know these things, but just now a less well-known things is now let's consider a field theory, a massive field in this metric. Oh, excuse me. Before I forgot to say one more important thing, one more important kinematical thing. Before we go to dynamics of field theory. The Euclidean analog of this picture. So in Euclidean space, what happens to all these curves as you go to the Euclidean? For example, what happens to the light cone in the Euclidean regime, in the Euclidean section? light cone are these two lines. Yeah, we have a point here. So in this projection, if you have to understand it in the sense that you have two-dimensional complex space, and then you have various real hypersurfaces. So this is you consider x plus and minus as two independent complex coordinates, and this you consider as an equation to a hypersurface in this two-dimensional complex space. Two-dimensional complex space is, of course, the same as four-dimensional real space, and this condition selects two-dimensional sections, two-dimensional surfaces in this four-dimensional space, different surfaces, and the light cone under this projection to one of the surfaces becomes a point. Okay, and what happens to this hyperbola? Yes, you're right. They simply become circles. And as a result, in the Euclidean section of this theory, you actually polar coordinates are what is called geodesically complete. Namely, in the Euclidean space, there is one-to-one correspondence between points of the space and the value of the polar coordinates. So you cover, with these coordinates, you cover the whole space. It's not the case here. These coordinates actually covers only 1/4 of the space. Because, as you see, first of all, we have a constraint x1 is with this parametrization. X1 is always greater than x0, and x1 is greater than 0. And so basically, geometrically, you cover only this quadrant, this quarter of the whole space. And once again, it's separated by the horizon. So that's another. These coordinates are not geodesic. This space spanned. This space is not geodesically complete. Which means that another definition of geodesic completeness is that any curve can continue indefinitely and will have up to infinite length. But it's not the case here. I will return to this question of completeness of space later. But now we have to really look at the field theory. So consider massive field theory. In any metric, if you have, let's simply look at the simplest possible field. We have square root of g alpha beta, d alpha phi, d beta phi, in an arbitrary metric, plus m square root of g phi square plus interaction. Now, in our case, we have this term will give nothing because it's conformally Euclidean, which means by that I mean that you'll have e to the 2z from here and e to the minus 2z from here. So the action will be dt phi square minus dz phi square, so completely insensitive to the metric, but this term will be sensitive So I stress again that when Z runs, Z and T runs from minus infinity to plus infinity, they by itself, this thing is defines the complete space, but when they run in this arbitrary interval, they cover, from the original space, they cover only 1/4. And we will see how the reflection of it. Now, you see this field has a well-defined Hamiltonian. To go to the Hamiltonian depends on canonical momenta, pi of c, and canonical coordinate, phi of c. We have, if we go to the Hamiltonian, this is simply a harmonic oscillator after all. So what will be the Hamiltonian? It should be an integral over z of what? Go from Lagrangian to Hamiltonian. Yes, it will be pi square of z plus dz phi square. That's just the standard Hamiltonian for harmonic oscillator. The only non-standard thing will be that m square will come with this thing. So you see at the first glance everything fine, and the Hamiltonian is positive. What? Here, oh yes, right. It should be minus here. It should be a minus here. But the Hamiltonian is strictly positive, and it's very easy to quantize, actually, because all you have to do is just take the eigenfunctions of the, you write down the Klein-Gordon equation, the metric is time independent, and generally the Klein-Gordon equation is omega square minus p square minus m square psi is equal to 0. In this, with these modifications, we still can keep Fourier transform with respect to time, because nothing is time dependent. We have omega square plus dz square minus m square e to the 2z this is just the equation for the Bessel function. Psi, you can find that, you can do it yourself. It's just this, I think, called Macdonald function. And using these modes, omega goes from minus infinity to plus infinity here. And using these modes, you can find the green functions, you can quantize, and so on. So far, no surprises, but now we come to a really strange thing. If you do this quantization and you calculate the averages, you tend to assume that we are in the ground state of this Hamiltonian. We find the green function, which is easy to do. I leave it for your exercise to show that the green function is proportional to I shall return to this row smaller. this is the Bessel function at imaginary argument. You can easily solve this problem and show that this is the case, and that all Feynman diagrams, they are well defined. You just use, instead of flat space propagator, you use this one. And the surprise is that you will get, in fact, incorrect answer in this way. And that we will analyze now. And the incorrect answer comes because this space we are discussing is geodesically incomplete. The right answer, by the way, I should tell you that it's not completely solved problem. There are still a lot of things to be clarified in the solution of this problem. We will see that it deals with the wrong vacuum, that going to the accelerated frame can change the vacuum. And what I will try to show you is that the right vacuum, that just like the part when you go to accelerated frame in the normal fluid, in the normal phase of the superfluid, you will start creating elementary excitations, and you will end up with something very interesting here. The correct green function will be the green function at finite temperature. You will, when you go to the accelerated frame, in this case you create a finite temperature related to acceleration, which is called the Unruh temperature. Unruh, the guy who noticed this first. So how to see that this is the case? So once again, what I want to demonstrate. Let's summarize again the situation. We have a system with positive, well-defined Hamiltonian. However, the claim is that this ground state is unstable, and when we go to the accelerated frame, we actually have the green function, the correct green functions are not the green functions calculated with respect to the ground state of this Hamiltonian, but the statement is that the correct green function will be which by itself is quite curious, because instead of pure state green functions, we get a mixed state. It's a density matrix which is responsible. So let's demonstrate it correct green function are the green functions measured by the accelerated observer, and that I will demonstrate this. In other words, the statement is that despite positivity, this Hamiltonian is not stable. It creates excitations. So the dynamics of this, surprisingly, the dynamics of this creation of this instability is very poorly understood up to now. Okay, now let me formulate what I call the correct result. That may be partially answer your question. Let's suppose that we are in the complete space, and let's assume that this complete space is in the ground state. Therefore, it is described by the green function. When we have the green function, it will be simply the function of the interval x1 minus x2 square. That's the property of the ground state, because if you have finite temperature, it's not true anymore that the green function or in some excited state, it will not be simply the function of the interval, because it's only the ground state which is invariant under Poincare group, under the whole. And that's what we call the green functions, the correct green functions, assuming that the whole Minkowski space is in the ground state. And then let's write down x1 minus x2 square in the following way. Let's write it down as x1 plus minus x2 plus, x1 minus minus x2 minus. Now we have x plus in general is e to the z plus or minus x plus or minus t. So we will have z1 plus t1, z2 plus t2 multiplied by e to the z1 minus t1 now we get, let me see, e to the 2 z1. When we multiply these two parts, we get e to the 2 z1 plus e to the 2 z2 minus e to the z1 plus z2 multiplied by e to the t2, let's see, t2 minus t1 plus e t1 minus t2. I'm going to now simplify this, and we get the relation is between the coordinates is that it's e z1 plus z2 multiplied by cosh z1 minus z2 minus cosh t1 minus t2. Oh yes, it's tau. I hope I didn't make any mistake. I think I didn't. T2, okay. And now the interesting thing is that if you go to imaginary, the basic reason why for the statement of this temperature is that this green function is periodic in imaginary time. As you see, it's periodic if you change tau 1 plus 2 pi I. And now I shall explain you very briefly the well-known fact that periodicity in imaginary time means temperature. So, but before I explain this, let me formulate the statement. The statement is the following. The statement is that if you there is a green function. Let's suppose we have for 1 second. Suppose we have the. It's not really necessary, but to visualize it's better to have massless fields. For the massless field, well, I probably should keep it this way. We have the green function, which is the solution of this Klein-Gordon equation. You can select green function. How, by the way, when you the easiest way to, when you have Minkowskian space, the easiest way to select the green function corresponding to the ground state is what? How would you have, suppose you have a problem in front of you. You have the Klein-Gordon equation. There are infinitely many different green functions because they all can differ. There are many solutions of the homogeneous equations. So how would you select the green functions for the ground state? For instance, how in the harmonic oscillator, if you have harmonic oscillator, then the green function is the correct green function. Correct means the ground state green function is this. And how you can sure, you in principle you can add various exponentials e to the I omega t, and it will still be a green function. So in which way how would you select this one? Yes, it's the best thing is to look at imaginary time. So you take t greater than t prime, which means that your function is phi of t prime, and the ground state will come with the exponential e to the I omega t, so that it will be possible to analytically continue it. It tends to 0 as t goes to minus I infinity. And so you first take t greater than t prime, or the opposite way, and then you check whether your green function vanishes at minus I infinity. Why is this true? Or in other words, you check that your green function contains e to the minus I omega t and does not contain e to the plus I omega t. E to the I, that's the formal way of saying this. It's a very simple argument from the spectral expansion. The spectral expansion tells you that it's 0 phi n square e to the minus I n minus I0 t minus t prime. So when you are if E0 is the ground state, this is always positive. And so you can continue down this green function. If you are not in the ground state, that's simply not true. Now, analogous statement for finite temperature is periodicity in imaginary time. I will probably tell you a few things about it. So now, in this way, you can make sure that this green function is the correct one, is the ground state green function. But the ground state in these coordinates in the accelerated frame, I call this set of coordinates accelerated frame. The ground state in the accelerated frame here is not Minkowski ground state. So if you have a region with the Minkowski space and you have a field, which is and field theory in the ground state in the Minkowski space, and then you look at it in the accelerated frame. What do you see? You see the finite temperature, because this thing becomes periodic, which means that the to put it into more words, when you take this green function and restrict it to the accelerated frame, this is sometimes called the Rindler wedge. So you restrict it here and translate it into coordinates corresponding to acceleration, to accelerated frame. You will find that in the accelerated frame there are finite temperature green functions. That's surprising by itself, but that's not the end. I promised you to explain it from the point of view of Wilson loops, and I will. The more physical way, and that's, by the way, I want to stress the analogy that you go in the superfluid case, in the normal phase, you go to the frame, you start with the ground state. In the original frame, you go to the moving frame, and you find that the fluid is in excited state. You find that elementary excitations have been produced. And that's the analogy here. By the way, probably to make these things more interesting, is after you understand well these accelerated frame things, precisely the same. There will be very little difference with when you consider black holes and the de Sitter space. The idea is basically the origin of the mechanism. It's basically here, and it's common to these cases. Yes?
Galilean transformation cannot produce finite temperature.
No. Well, in a sense, it depends. If you if you wait long enough and you generate many elementary excitations, they interact and they thermalize, basically. After they the difference is that here thermalization occurs without interaction. It's property of the background, this thermalization. But there's, plenty of things to be understood better than they are now. And that's why I will now explain these things from a different point of view.
If you think about the thermalization process,
yes.
You are actually ignoring some of the details, and you go to the mixed state because you are ignoring some of the information.
But this one is just a quality transformation. You are not losing any information.
Well, here, very good point which you are making. I really appreciate it. But you see here, you are in a sense ignoring. You are saying that the reason for thermalization is the fact that what happens beyond this Rindler wedge is inaccessible to this observer. Namely, I just started saying. I just started the whole discussion with saying that we have a horizon here, which means that any observer in accelerated frame will not be able to receive signals from the observer at rest. And this lack of information, and so you, in a sense, when you calculate the green function here, you average away all you don't know. And that's what replaces what leads to thermalization in this case. But yes, there is this difference. The difference indeed is that here is geometrical inaccessibility of this part of this. Whatever happens to this observer is not really felt by the accelerator.
The signal would immediately before time is equals to 0.
What? Oh yeah. Sure. You're right. If you have here
This was confusing me.
now you see it, now you don't. You know? You do see it before time 0, but you don't see it after that. Quite amusing, I think. Now let's look at it from the different point of view, from the point of view of the accelerated observer, which goes along the hyperbolic trajectory, keeping a thermometer with him. The statement is that this thermometer in the hands of accelerated observer will show this temperature. Let's try to, that's one thing which we will discuss. And the other thing is suppose it's a slightly different one. Suppose we have an electric charge performing this motion. Is there radiation damping in this case? Let's discuss both things. First of all, let's talk about. Remember, last time we looked at the static particles, and we said that while in relativistic case interaction we have Dirac fermions, they interact in some beautiful way with electromagnetic field, and so on. In the semi-classical limit, if those fermions are very heavy, you replace it by a much simpler Lagrangian. Namely, we this thing, S is a proper time, and we have the term A mu of x of s, dx mu ds, psi dagger psi. For scalar field, dx mu ds, now the spin of this guy will not concern us at this point. We will look at the following situation. Suppose that static particle has two states. So let's look at the following model instead of this. So, excuse me, let me stress one more thing here. So this is what happens to this. Is basically this diagram when the particle moving along some trajectory emits the field. And that's the amplitude. The probability will be proportional to this guy, where we put the delta function here. So it's basically what I mean is you take this, you take square, and you sum over final state, and you have this diagram with imaginary parts of the green functions. That's the general thing. The only difference with this diagram, with the general Feynman diagram, is that there will be the same picture, but we will have here relativistic propagator, and it actually reduces to the to this thing. And for instance, to make it more clear, if you emit a photon, you have the following. You have the current here is integral dx mu ds delta of x minus x of s, and emission of the four-dimensional photon will be this diagram will be related to with momentum k. Suppose we emit the photon with momentum k. J mu of k will be, here's integral over ds, dx mu ds, e to the I k x of s. And that's what is called in string theory the emission, the vertex for photon vertex. Now, what's the how to calculate the classical probability that a particle emits the photon? Particle moving along particular trajectory emits the photon. What is the probability? So I'm asking about the value of this diagram. This guy, this current is just this one, with this representing a static particle. And that's classically we don't consider quantum particle emissions. We just look at the particle moving along some particular trajectory, emitting light, emitting Bremsstrahlung radiation. It's a Bremsstrahlung radiation. So what will be the answer for the probability? dW will be proportional to what? There are, of course, many pi's and etc., which I'm not asking you about, and I don't remember them myself. But that's not what concerns us. How, knowing this current, you calculate the probability for emission of photon?
Current square.
Yes, it is a current square, but what else? What else is, yes?
Density of state.
Yes, density of states, which you can write down in several ways. You can, for example, write it down as theta of k0, you emit on the positive frequencies, delta of k square d4 k. And which is, of course, you can also write it down as d3k divided by the absolute value of k when you remove this delta function. That's the relativistic density of states. You were right. It's just the density of states which you multiply. And now a slightly less, why I am talking about this, what it all has to do with the Wilson loop. Rewrite this as a will, or even more than that. How would you rewrite it as a Wilson loop? As some kind of Wilson, not precisely the standard Wilson loop, but okay, that's probably an unfair question, but if you can ask, it's. So we have this contour. See, it might be closed. I don't care at the moment whether it's closed or it has. It's better to have it closed. It's simpler, but that's not my concern now. j mu of k is this integral along the contour. So we can write it down as integral over ds e over dx mu e to the ikx and integral over the contour. Now, since you have the square, you see you have dx mu, dx prime mu, e to the ik x minus x prime, multiplied by theta of k0, delta of k square, and let's integrate it over d for k to get the complete amplitude. And now it's probably, it is almost the standard Wilson loop. I shall let me give you a hint. The standard, yeah, the standard Wilson loop.
It's like for free field, right?
Yeah, I'm talking about the emission. Or you have photons are free.
Yeah, it's in last lecture, just average of some fields. If you will integrate over okay,
Yes.
you will get some propagator basically.
Yes, exactly.
Yes.
That's the point.
Average.
But let me remind you what the standard Wilson loop, which you define, say, in Euclidean or in Minkowskian, in the first order. So this is the e to the I integral over c a mu dx mu, and that's w of c, and the first correction to w of c to the Wilson loop. It's the e-square correction is given by this diagram. You exchange the photon here. This what I'm saying here is highly non-standard. What I'm saying here is something you find in many textbooks. It's standard stuff, and I want you to compare the two. So we have the ordinary Wilson loop with which we study confinement, for example, is simply dx mu, dx prime mu, x minus x prime square minus I0, which is the propagator, photon propagator in 4 dimensions.
Basically, the e to the power of this.
Yeah, it's a correction. So you expand. It's not. It's actually, remember I told you the rule for the Gaussian. You first expand it to the second order and then average, then exponentiate back. That's the way you. So there is a close connection between these two guys. And for that you have to figure out, you have to calculate the in this case we have theta of k0, delta of k square. In this, what replaces it here is that this we simply have the Feynman propagator d for k, k square plus I0. And the difference, first dimensionally speaking, it's clearly the same thing. It's from the point of view of scaling of dimension. It's d for k divided by k square. So you have k 1 over x, and that's why you get 1 over x minus x prime square. The difference will be only with a complex, with the way you go around the singularity.
Here it is delta, the delta function.
Yeah, but
yeah.
it's the delta function also has dimension.
Yeah.
So So now it's very easy to see what kind of imaginary. The answer will be. I shall write the answer and explain it. It's t minus t prime minus I0 square minus x prime square. So the only difference is that I0 here stands out of the brackets. Here it's in the brackets. Now you probably can explain to me why it is why this thing should have this form. It's very simple argument.
The theta function.
You see, right, theta function tells you that k0 is always positive. So you have the exponential k0 t minus t prime. And so you can always add plus I epsilon here with improving convergence. And that's, so I probably should have put plus here, but that doesn't matter. So basically, you have the integral of the same type, if you want to know the decay, the probability for a particle to perform Bremsstrahlung, you have to calculate this modified Wilson loop. And the answer will be dx mu dx prime mu x minus x prime plus I eta square, where eta is that's more covariant. Where eta is a vector, it's time-like vector, any infinitesimal time-like vector. While here it's the same expression. So this is the probability for emission. And now we can also calculate very easily. I hope I didn't. Oh yeah, I didn't. We can calculate very easily how much energy was emitted. We will use this formula to calculate the how it's called, the radiation damping for the moving particle. So that's what I was telling you from the beginning, that the Wilson loop itself, the original Wilson loop, measures basically interaction energy between quarks, while this modified Wilson loop, which is quite interesting, in principle it measures emitted energy. It measures non-equilibrium phenomena. So how to, if I want to find emitted momentum, not simply probability, it's extremely simple. How would you modify this integral to get p mu averaged? Very simple modification, very concrete. What should I do with it? The emitted momentum is momentum of the photon, it's k. So I simply multiply it by k mu and then integrate over. But multiplication by k mu is just differentiation of this guy with respect to x. So we will get some very simple formula. Now, it's very interesting that without this thing, you see this integral, this double integral, will be zero. if you put I epsilon here, it will be 0 because this would be even, while this is odd. So we will get 0. However, with this imaginary part, it is well defined, and I will not go into this. It's getting later as usual. But will not go into this. But you can derive an interesting formula, namely that I suggest that you try your hand at this integral and see that this is true. Namely, the radiated momentum will be integral over ds of the terms of the type of the type there will be x mu triple minus some terms like x mu something like that. I'm not completely, don't quite remember. There will be some combination of this local expression. The key point for the calculation, if you care to do that one, is that the imaginary, it's only the imaginary part of this which contributes, but the imaginary part is the third derivative of the delta function. So you will have the delta function here. Okay, that's I said a little bit more than I wanted to because while this Wilson loop are important to see to see that the observer will be thermal, the thermometer will show the temperature. It's also I actually plunged into the things which interest me very much, namely this still incompletely investigated phenomenon of radiation friction. But okay, let's stop here. It's getting late.